All right, so here's just a quick tutorial on this response surface-based Pareto front generator. And what it allows you to do is you have competing outputs that you want to optimize. For example, you want to minimize stiffness and minimize mass, and those are competing outputs, and it gives you a trade-off curve between those values, or the Pareto front. So I'll give you a couple examples, concrete examples, so you can see what I mean there. But first, we'd look at how we format the data. So it accepts, design experiments type data, which I'm going to use data from simulation in SOLIDWORKS, but it could be measurement data or simulation data. And you're going to have one or more inputs and at least two outputs in order to make this work. And in your data, you're going to set it up in a spreadsheet. Here I'm using Excel, but you can use Google Sheets or something. And the data format it's looking for is the first row needs to be headers or labels for your data, and your data is below that. And then you don't want any extraneous stuff outside of the data on your spreadsheet. It's just going to use the first sheet if you're using an Excel sheet, spreadsheet file. And so important thing is the first row is headers. If you don't have headers in the first row, it's going to use your first row of data as headers, and that's not what you want. So you want headers. You can edit those, as we'll see, and then the data below that. So that's the format you want. There's multiple ways you can bring that in. You can input the file directly. If I hit the browse here or browse here, it's going to do the same thing, and I can go directly to that file, response surface CSV I'm using in this case, but it'll open an Excel file as well. Another way to bring in a file, I can hit reload to get back to that initial page, is to just click and drag a file from my file system onto that box, and I'll do the same thing as the browse import does. Probably the easiest way to bring in data is just to cut and paste it from a spreadsheet, and you can do that either from the initial page, and so here I can grab, do a copy. In this box, just do a Control V of what you copied, and it's automatically going to bring that in. Also, when you're here, you can paste as well in any of these cells, and that will paste the whole spreadsheet. So it would say I just wanted these first, these three columns. Then I can click on any cell here and do Control V, and that's going to do the same thing. But let me get back to that original data set here. So I'll grab all the columns, Control C. Click on any cell, Control V, and that's going to replace the whole table. I can make edits to the headers here. So if I wanted to add units, for example, I can add those, rib depth in millimeters. The headers are important because those will use to label your plots later on. And so those labels get pulled through. So you want to have them, the way you want your plot labels, what you want to have here. And so if you want to add units, you can, or change names, you can do that here. All right, and so just to do an example that you can follow along with, I have these two buttons here of two example data sets, which shows some different features of the Pareto front generator. Important thing here is you're doing a quadratic response surface fit to the data. So there's an underlying assumption that the data is fairly smooth, that a polynomial fit will do a good job of approximating the data. It's doing a least squares fit of the data with a second order polynomial between the inputs and outputs as the response surface. So it'll work with data that's not smooth, but it's just going to be a best fit to that data. So it's going to be the results are going to be most meaningful for smooth data, and usually for kind of structural analysis examples like I'm showing here, that assumption holds. So I'm going to click Hold Panel Example Data Set, which is actually the same data set I've been working with in the spreadsheet. And that's going to load that example so you can follow along. And so let me show you quickly what we're looking at here. And so this is this panel, ABS panel. We're adjusting the rib height and material thickness, so it's like an injection molded panel. And we want to, the competing outputs are, we want to minimize mass but while remaining as stiff as possible. So those are our competing outputs that we're going to look at a trade-off curve for. And this is a full factorial DOE that I'm doing here, and I was done using a design study in SOLIDWORKS, but it could be any simulation data or measurement data, like I said. But this is the example. So we want to find, optimize rib height and material thickness to generate that trade-off curve between mass and stiffness. And the stiffness will come through as displacement, so we want to minimize both displacement and minimize mass. And so what you need to tell it here is what are your inputs and what are your outputs. And so that's what this choice is here. So we have inputs, material thickness, input is rib height. It gives the upper lower range. Usually you want to leave that as a default. That's the upper and lower range of your input data. So that's pulled in automatically. Sometimes you may want to fix one of these parameters. So if I wanted to say, well, let's look at a case where material thickness has to be 5, so you can do that as well. If you make them both equal, that's like a setting equality constraint on those that data. But usually the lower limit, you just want to leave those as your input range. You usually don't want to go beyond your input range because then you start extrapolating your data and the accuracy will drop there. And then you list your outputs. So you need at least 2 outputs to kind of continue on. And you tell it whether you want to minimize or maximize those outputs. Here in this both case for displacement, I want to minimize displacement to maximize the stiffness. I want to minimize mass. You need at least 2 outputs because we're looking at a trade-off between those outputs. And then we go kind of progress through these tabs here. So I'm going to go to the Pareto plot. If you don't have 2 outputs, so if I say ignore this one, it's going to tell you need to select at least 2 non-target outputs. So I want to do output. There's minimize, maximize, or target. We'll talk about target in our next example. So I'm going to minimize both those goals. So that allows me to set the X and Y axis for my plot. And so I'll just do one of your outputs is going to be X-axis, one of your outputs is going to be Y-axis. Getting a number of Pareto points here, default is 10. We'll start with that, and we'll click Generate Pareto Data. Actually, this is running Python on your browser. There's nothing sent to a server. This is all happening on your browser. It's using Python, using the Pyodide project that's running Python in your browser, using optimization routine from the SciPy library. And so you can see these are the original data points. And if you hover over the data points, these are just the ones I imported, the ones in orange. And those are from my original data set from the DOE. And then the Pareto front, by trying to minimize both mass and displacement, kind of systematically kind of iterating through the different displacement values, gives me this curve. And you can see it's kind of leaving out this point, and that's just because I don't have enough resolution. I can increase the number of points to kind of get closer to that point, but it still gives me a fairly good approximation of my Pareto front here. Each of these is a design point, so there's a specific height, material thickness, rib height, and then displacement and mass for each of these design points. You can hover over those points and see that. Once you've generated a plot, this last table will include the Pareto points as well. So if you want to do some more plotting of those in Excel or something, so I can Control C to copy those. And if I go to my Excel spreadsheet, add a tab, I could paste that here and look at it that way, or you can just export as CSV by hitting that button. You can download it as a CSV file. So you can see there's 2 different slopes here, and often that happens when you're hitting different boundaries on your input space. So I have boundaries, material thickness 2.5 to 7.5, and rib height of 7 to 15. And so here, if I go along these points, I can see that my material thickness is at its limit of 2.5, so that constraint is active. And as I switch slope here, now the rib heights become the active constraint. And so those different constraints will kind of create the boundaries of your Pareto front. And I can up the number of points. It'll take longer if I do more points, but if I do 100 points, the basic shape will be the same. It's updating the plot here. It takes a while. It's running Python on a different thread using a web worker, but still all local on your machine. And so here is that kind of, it's getting closer to that point there as well. So a better approximation of that Pareto front. Now it's important to note that each of these points is coming from a response surface. So you would want to plug these numbers back into SOLIDWORKS in my case, this material thickness and specific rib height if I wanted this design point, to verify. The mass is going to be pretty close because that's a fairly linear relationship, but the displacement might be a little bit of error there. So you need to do that verification run in SOLIDWORKS for each of these points because they are approximations, interpolation of your data set using that response surface. Let's pull in the second data set, and we can use that target option for an output. So I'm going to load the bottle example data set. So this one's a little bigger. It's actually full factorial, but you could do a central composite design. You don't need to have full factorial. This has more inputs, so it's more data points. And just to show you the model for this one, so here we're looking at a bottle. And what we're trying to do is keep a minimum stiffness for the bottle, again looking at displacement versus mass as their competing outputs. But we do have a third output, which is the volume of the bottle, because as we vary these 3 inputs, the thickness of the wall, the rib depth, and this diameter, the volume of the bottle is going to change. And obviously we care about the volume. We're designing it to be a specific volume, so the volume has to be one of our outputs. So we have 3 outputs: of volume, displacement, and a mass of the material. And so I just hit load bottle example. Now, sometimes we have data we don't want to use at all, like a run number here. There's 2 ways to ignore it. You can just not select anything. It's automatically ignored. Or I can directly choose ignore parameter. Each will do the same thing. And I tell it the inputs: thickness, rib depth, and diameter. Now, volume, I have 3 outputs. Now, it's only going to do a trade-off between 2 outputs. And the third one, it kind of ignores unless you set a target. And so what I want to do is, I'm going to look at the trade-off between displacement and mass. Again, I want to minimize both those, but now I have volume. And I want to have that as an output parameter, but it doesn't make sense. I'm not trying to minimize volume. I'm not trying to maximize it. I want to set volume for the design point of this bottle. And this shows you how you can handle more than two outputs when you're doing this optimization. So it doesn't make sense to maximize or minimize. So what I'm going to do is choose target. I'm designing for specific volume, and this is in millimeters cubed. So let's say we want to do a 0.6 liter bottle, and so that'd be 600,000 millimeters cubed. So I'm going to set a target for that. So that's going to have a constraint that the volume has to be 600,000. Now, the interesting to note here, none of the volumes in my design study are 600,000 because it's kind of randomly varying. And this is also a good way, if you have a parameter that depends on your inputs and you want it to be fixed, it allows you to do that. So none of our inputs are actually at the 600,000. So then I go to Pareto Plot. Again, so I choose my X and Y axis. For that, basically it's what's going to be X and Y axis on that plot. I'm going to drop this number of points down to 10. Otherwise it'll take a while. This one takes a little bit longer to run, and I'm going to hit generate Pareto data. And you can see it's updating plot. It's going to take a little bit on this one. And again, this is running Python in your browser. And so here is that Pareto front. Now it's just a straight line. And I'm at the minimum thickness for all of these, actually. 0.25 should be my minimum thickness, yep. So I'm at that constraint, is active for all of these. And it's varying the rib depth and diameter. And you can notice that each of these design points has a volume that's almost exactly 600,000 milliliters, even though all my inputs are kind of all over the place. And so what that does is allows me to kind of have one parameter fixed while I'm optimizing the other two. So it tells me I can have a bottle with low displacement. It's going to have a little bit more mass. And actually the slope is pretty shallow here, so I'd probably go towards the left here. And it's because it's taking advantage of that rib depth to really increase the stiffness of the bottle. And you can run different scenarios. So if I wanted to run at 500, like a 0.5 liter bottle, I just change that number here. Each time I change anything, the plot's not going to update automatically, so I do have to hit generate. And it's going to update the plot. While it's showing updating here, the plot's the previous plot. And what we'll see, it's going to be a little bit of a shorter line. It should be dropped. So it did drop down, you see, in mass, which makes sense. You're going to have a lighter bottle with less displacement, so a stiffer bottle with less volume. There's less designs here just because I'm really at the limits of my design space. So I'd have to allow for a thinner bottle or for deeper ribs in order to kind of have more design points. But it allows me to look at different volumes, what's going to be a trade-off between volume and mass of my bottle, the amount of material required. Okay, so this shows you how to use that Pareto front tool.